This talk, as Emil said, is about virtualization and about improving performance of virtualized systems. So over the past decade, virtualization has clearly had a significant impact in the server world. It went from being more or less a curiosity about 10 years ago to being the common case today. Now, because most of the world's server workloads now run in virtual machines, it is increasingly important to make sure that they run efficiently as close as possible to native speed. In fact, some of the remaining workloads that haven't yet been virtualized are latency-critical workloads for which performance matters even more. So what is virtualization? As probably most of you know, virtualization allows you to run multiple guest operating systems on the same physical host, sharing the physical resources on that host. And this is done using a thin layer of software called a virtual machine monitor, or VMM, that abstracts physical hardware. It does that by intercepting sensitive instructions, such as privileged instructions or instructions that touch shared resources like I/O devices. Now, in the early days, virtualization has resorted to binary translation as the mechanism for intercepting sensitive instructions. More recently, CPU vendors have added hardware support in the form of hardware-assisted virtualization, or HV. Now, how does HV execution work? Well, most of the time the guest runs on native hardware, roughly at native speeds, in the so-called guest mode. Every time the guest encounters one of these sensitive instructions, hardware automatically transfers control in the VMM. And this transition from the guest to the VMM is usually referred to as hardware virtualization exit, or for short, just exit. Once in the VMM, you just handle the instruction, emulate the effects of that instruction, and then resume back to the guest. Now, hardware-assisted virtualization is great. It makes it easier to write VMMs because you focus just on the way you handle instructions rather than focusing on a mechanism to intercept instructions. And typically, for most workloads, hardware virtualization, HV execution, outperforms classic binary translation. So this is great. However, hardware virtualization also introduces a new problem, namely that exits are expensive. So this table here shows the cost in cycles of hardware transitions between the guest and the monitor, the latency of an exit-resume round trip in hardware. Now, this is for different versions of the Intel CPUs. The numbers for AMD are roughly the same. Now, as you can see, these numbers are fairly high, and it has been quickly realized that the high cost of exits is a significant problem, is the major source of virtualization overhead. As you can see in this table, hardware folks have spent a fair amount of effort across releases to bring these numbers down. However, the numbers are still fairly high, and as this table shows at the bottom, this suggests that the trend here is that they may not get much lower. There have been also other approaches that hardware designers have taken to address this problem. For instance, eliminating certain kinds of exits using hardware support for paging, also known as nested paging. Now, in this talk, I will present a complementary software-based technique to this problem. The observation here is that sometimes multiple exits happen in quick succession, one after another. The guest makes little progress, and the time is mostly spent into the transitions between the guest and the VMM, essentially ping-ponging between these two domains. What we propose is to enhance the virtual machine monitor by detecting such cases and grouping together the exits, or cluster the exits together. Execute all of them together in one shot before returning back to the guest. So this is the high-level idea of what we're proposing here. So this is the outline of the rest of the talk. I'll start with what we call exit pairs. This is a very simple form of the method that I'm presenting. Then I'll generalize to exit clusters. Then I'll talk about nested virtual machines, which are a use case where this method actually works quite well. And in the end, I'll briefly go through some results and discuss some future directions of work and conclude. Okay, so let's start with this example here. This assume that you have a 32-bit guest operating system running with physical address extension to address memory to address physical memory beyond 4 gigabytes. Now, with physical address extension, or PAE, the page table entries are 64-bit wide, and the 32-bit guests typically update this using two back-to-back 32-bit memory writes. This is what these two example instructions shown in the left of the slide are. Now, if the VMM is using software support for paging, also known as shadow paging, each guest access to a page table is intercepted, and the monitor updates its own copies of the page table, namely the shadow page tables. So in a system with HV, the execution works as shown in the slide. The first access to the page table, the first move instruction, causes an exit to the monitor. The monitor intercepts that, emulates it by updating the first half of the PTE in the shadow page tables, and then resumes back to the guest, only to exit right away back to handle the second half of that PTE. So what we can do here instead of this is the following. When we get the exit on the first move instruction, the monitor, the VMM, can peek at the next instruction in the stream, and if that turns out to access the adjacent byte, then it can conclude that that will also exit. So it can emulate the effect of both of these two writes in one shot before returning back to the guest, thus eliminating the middle transitions in there. In fact, in this particular case, it can do even better. Instead of calling twice into the shadow page table subsystem, for two 32-bit writes, it can actually even optimize the handling of those two instructions in one shot with using a single 64-bit update of the page tables. So this is a very simple form. Now let's see how we can generalize this to more than two instructions. Well, the idea in the general case is as follows. Whenever the monitor, the virtual machine monitor, gets an exit, what it does, it starts looking down in the instruction stream. It inspects the next few instructions. In our implementation, we look at the next 16 instructions. And then it tries to reason about the exit behavior of those. Do they exit or not? And based on that, it tries to group as many of them as possible. Well, it tries to group as few as possible to eliminate as many exits as possible. All right. So this is and once you form this group, then you can handle or emulate the entire group together before resuming back. The challenges here are how to form these clusters and how to make sure that the overall execution is efficient. So let's go through another example to illustrate this. This is in instruction in the guest, and since it performs I/O, it is intercepted by our monitor to emulate this its effect. So this instruction causes an exit here. The VMM goes and peeks, decodes, and analyzes the following instructions in the instruction stream. For the sake of simplicity, I'm only showing here 8 instructions. As I said, in practice, we're looking at 16 instructions downstream. Now we try to reason about each of these, if they will cause or not exits. All the instructions shown in blue here are I/O instructions. They will all cause exits. All the other instructions here, shown with gray, are ALU instructions that would not cause exits when run in guest mode in HV. So based on this information, we want to group together multiple of these instructions to eliminate exits. Well, the last 2 instructions here, there is no point of including them in this group because they will always run faster on native hardware than emulated in the monitor, right? But we want to extend the cluster as far as possible to include all the blue instructions in here because all of these are causing exits. So we form a cluster containing the first 6 instructions here. Now, the 2 instructions in the middle, the two instructions in gray, they do not cause exits, but still we include them in the cluster for the benefit of eliminating the exits on the last 2 instructions. We call these instructions gap fillers. These are separating the exit-causing instructions in the stream. And the point that you should keep in mind here is that these 2 will execute slightly less efficiently in the monitor compared to real hardware. But here, we're doing this to eliminate the exits on the last two instructions. So another way to think about it is by eliminating exits in here, we come up with a certain budget that we can spend. And as long as the emulation of the middle instructions does not go over that budget, then the entire transformation is profitable. So once we have this cluster, we can execute all these 6 instructions in one shot and then resume back to the guest after the 6 instructions. So this is how we formed here the cluster. Now let's turn and look at efficiency considerations. So the first thing that we want to make sure is that we don't spend all this work of analyzing, decoding instructions, and forming clusters every time we reach an exit at the in instruction here. That would be very inefficient. The other point here is that a simple implementation of emulating the 6 instructions would be just to interpret each of those. Again, these would be fairly inefficient, especially for the middle 2 instructions, which would otherwise run directly on hardware. So to address these 2 issues, what we are using is a translation of the entire cluster, pretty much pretty similar to the standard classical binary translation. So we take the 6 instructions, form the cluster, and we generate a translation for them. We put that in a translation cache. Every time the monitor gets an exit, it looks up its translation cache to see if there is a cluster already formed at that address, and if so, it reuses that work. So another way to say this is that we pay the price of translating and generating code only once, and that is amortized over many subsequent executions. In fact, the cluster translation starts with a preamble where it checks first if the bytes in the translation have not changed since translation time, and then that is followed with the actual translation of the cluster. So in this example, there was one part that made things a little easy, and that is that it was straightforward to see what instructions will cause exits and what instructions do not cause exits, and determine this information at translation time. This is not always the case. So here's another example with 10 instructions. The instructions highlighted in blue are causing exits, including the first one here. The ones in gray are ALU instructions. They do not cause exits. How about the remaining 2 instructions, highlighted here in red? These are memory accesses. Do they cause exits? Well, it depends. If they touch memory-mapped I/O devices, then yes, they will cause exits. If they touch page tables and the system is using shadow paging, then yes, they will cause exits. But if they just touch regular stack or heap memory, then they will not cause exits when executed in HV mode. Right. So this is it's important to know their exit behavior because that's what we use to determine how big this cluster will be. Right. So we use the following terminology here. We call instructions such as in, out, or other similar instructions. We refer to them as strongly exiting instructions. These are instructions that the translator can determine, that can label as exiting just by looking at their opcode. On contrary instructions such as memory accesses are referred to as weakly exiting instructions because their exiting behavior is dynamic. It depends on the runtime. So the way we address this issue in the translator is using a runtime approach that we refer to as dynamic cluster formation. The idea here is to tag each instruction with an exit count, the number of times an instruction has exited. When the first instruction in this sequence here, the out instruction, causes an exit, we do not proceed to form a cluster right away. We postpone the cluster translation. We just handle this one instruction. We actually interpret this instruction, and we increment the exit count for the instruction. And the idea here is to collect some information to postpone the translation and collect information about the exiting behavior of instructions downstream. So we let the system run like this for a while, and after a certain amount of time, namely in our implementation, after the first instruction here causes 3 exits, we decide that we have gathered enough information and we are ready to proceed with cluster formation. So in this example, when the first instruction reaches the 3rd exit, the exit counts of the instructions downstream look as in this slide. Namely, we can see that the first move instruction in here has a reference, an exit count of 0. It probably accessed just a stack variable. Whereas the last instruction here has a reference count of 2. It caused exits in the past. So based on this information, we can now form a cluster including all instructions to save exits both on the exit and on the second memory access here. So this is the idea with dynamic cluster formation. The next thing to consider is control flow. All the examples that I've shown so far are straight sequences of instruction without control flow. We have extended this technique of clustering to include branches, both forward branches and backward branches, loops within clusters. There are a number of issues to consider there, including issues regarding strongly and weakly exiting instructions, but I will not go into those details, but you can find all these details in the paper. What I should point out, though, is what I should highlight is that although we are looking only at small sequences of 16 instructions, one may not expect too much control flow in there. However, that was not really true when we looked in practice. This is a cluster of 15 instructions that has surprisingly complicated control flow. I don't expect you to read what's in there, but just highlight that there's just 2 exiting instructions in blue here and a lot of control flow, including a bunch of nested loops in there, all within just 15 instructions. Okay, now let me turn the discussion to nested virtual machines. So what are nested virtual machines? Well, with a nested virtual machine, you run the hypervisor and the guest on top of it, to which we refer as the inner guest, all together within an outer virtual machine, which is the that runs on top of an outer VMM. There has been recent interest in this area, and applications include scaling, simulating large-scale virtualized environment with fewer physical hosts, demo or training people in virtualized environments, or testing and debugging hypervisors. There's also so-called Windows XP mode in Windows 7 that runs older applications in virtual machines. So if you want to run Windows 7 in a VM, then the Windows XP mode will become a nested VM. So how do exits and hardware-assisted virtualization looks like with nested VMs? Well, for the outer VMM, things look just as they were before. The transitions are triggered by hardware. The monitor exit path does additional software work and then handles the instruction, all on bare metal, on hardware. For the inner VMM, things are quite different. The virtual hardware exits are now emulated in software, and therefore they're much slower. To make things even worse, the exit handling path of the inner VMM touches a lot of privileged state and causes a lot of exits on the outer monitor. So even the software part of an exit is slowed down. Putting these things together, the overall overhead of an exit is pretty much an order of magnitude bigger than the overhead of an exit in the outer VM. To say it differently, from the point of view of the inner VM, it feels like it's running on really slow hardware. From the point of view of the outer VM, it feels that a nested VM is a special workload that triggers very frequent exits. So the clustering technique that I described in the previous slides can make a big impact. And the interesting thing here, it can have a big impact at both the inner and the outer level. Right? The inner level, because these transitions are so heavyweight, eliminating some of them can have a big impact. Right? The remaining transitions, the remaining inner transitions that have not been eliminated by the inner clustering now cause frequent exits on the outer level. So if you cluster at the outer level, you can eliminate and improve things even more, right? So that's very interesting to point out. The other thing that I should point out is that the inner VMM can be written in such a way that the exit handling path, the sensitive instructions in the exit handling path, are packed together next to each other. And that makes it easier for the outer monitor to detect and to cluster them. So for instance, the exit path, the exit handling path of a monitor on Intel CPUs involves a lot of instructions called VM read and VM write that save and restore the guest and hypervisor state. If you put all these instructions next to each other, then the outer VMM can cluster them together. I should point out that this is not para-virtualization. The inner VMM just reorders instructions. It's not relying on any services from the outer VMM, and in fact, it doesn't even know that it's running inside the VM. Now let me give a few highlights from some experiments that we've done. All this, what I talked about today, is actually running currently on the desktop and server products from VMware, both Workstation, Fusion, and ESX. The implementation has gradually and organically evolved over many years and many releases, starting with the very simple techniques of pairs, then to all exiting sequences of instructions, then adding gap fillers, dynamic cluster formation, and loops. All of these have been added gradually over the years. Here's a few experiments for non-nested VMs. Passmark to the graphics benchmark. When running with clustering of exits compared to non-clustering, the benchmark score improved by between 50 and 80%, depending on the CPU. VMmark virtualization benchmark. Here we only looked at the workload aspect of the benchmark, not at the live migration or consolidation aspects of the benchmark. Although we have seen that clustering consistently drops the number of exits, we have not seen any measurable improvement in the running time. And that's because these workloads are not dominated by exits. So eliminating exits doesn't make a big improvement. Finally, we looked at an emulated E1000 NIC, and we looked at the exits on the packet round-trip path. So in this case, clustering made a difference of 24% in the number of exits on each round trip. Here's an experiment with nested VMs where the inner VM runs a kernel compile workload. These are the improvements in running time when clustering was applied either at the inner level, at the outer level only, or at both levels, compared to running the same VM in a nested setup without clustering at any level. Both for Intel and AMD. So you can see that with clustering at both levels on Intel CPU, the benefit is pretty significant. It improves the running time by more than 50%. On AMD, the improvement is slightly slower. Well, it's somewhat slower, mainly because AMD doesn't have the equivalent of the VM read and VM write instructions that I mentioned earlier. These are straight memory accesses that do not cause exits. Still, there were some improvement on the order of 20%, which is significant. So where do we go from here? Well, there are a number of things that can still be done to improve clustering. One of them is that currently we look at just a contiguous small sequence of instructions after the exiting instruction. So for instance, we cannot capture things like a loop where the exit is in the middle of a loop. This is something that we're currently working on. Also, there are opportunities to improve memory accesses. These usually require heavyweight calls into the memory subsystem, so we're looking into caching and reusing some of the work in the translation for memory accesses. Finally, we want to look closer at the impact of clustering on latency-critical workloads. So these are the main points that you should take from this talk, and with this I will conclude, and I'll be happy to take any questions.
Luigi Rizzo, Università di Pisa. I was wondering, from your presentation, it seems that checking whether an instruction exits or not is much cheaper than actually executing the instruction in the emulator. Is that true?
Checking whether the instruction exits or not, yes, but there is also work in decoding the instructions, and that is actually more heavyweight.
Okay, thanks. And second question. Is there any suggestion that you can make to operating system developers or compiler developers to reduce the number of exits or improve the clustering?
Yes, that's a very good point. Yes, perhaps that's this talk can be taken from both VMM implementers, but also for general system developers to understand what are the causes for slowdown or what are the opportunities to improve things. Yes, from a system development point of view, you should be aware of instructions like I/O instructions that cause exits. If you put them next to each other, there is a good chance that they will run faster on VMware products. You could even imagine a compiler that has a dash cluster option that automatically generates code that puts these things together. But it has to have knowledge about which ones cause exits, and different hypervisors trap different instructions, so it may be a little more difficult.
Hi, John Griffin from Telecommunication Systems. Question, I guess, sort of like Luigi's first question, which is, I'm curious a little bit more about the gap filler instructions. It seems a little scary that you're going to run, user code right down there in the hypervisor. I'm sure you guys have thought about this a bunch. Could you comment a little bit more on the security model there and the sorts of things you have to do to make sure that nothing bad happens?
I'm not sure what you're concerned about, the security of the emulation or about the overhead of the execution when it's emulated?
Well, I apologize, I haven't read the paper, right?
Sure.
So I was thinking, like, could somebody slip a halt instruction or something in there? Like, what do you have to do as you're deciding that it's okay to run gap filler instructions inside the hypervisor as part of your cluster? Is there anything you have to do special in handling those gap filler instructions?
Well, that's nothing different than classical binary translation. It's just emulating the effects on the virtual hardware. So for LE instructions, it's just about updating the virtual CPU state. There is nothing different than before. I don't think there's any security aspects to it. There's only this aspect of slowing things down because you're emulating them. But regarding that, there is something additional that you can read in the paper. Some instructions like ALU have very little emulation overhead. Others, like memory accesses, are actually very heavyweight. And with those, you have to be very careful. We have additional constraints, such as allowing only a few memory accesses in the gap fillers. We don't allow more than 3 memory accesses in the gap fillers. Yeah.
John Sopka from EMC. Could you return to your slide showing the nested VMMs?
Yes. The results or the VMs?
No, the diagram, this diagram here.
Sure.
I didn't understand the diagram. I would expect that when the inner guest triggers a VM exit, that the exit will proceed directly to the outer VMM. It's the only one running in the ring 0, isn't it?
So that's correct.
The arrows don't make any sense to me on this diagram. Is that just a shorthand to make the talk go faster, or could you explain that?
Yes, this is a very there's a high-level view of this. Yes, each of these heavyweight arrows traps down first on real hardware, and the real hardware decides to forward that to the inner guest or handle it in there, because both exits from the inner and the outer VMM goes directly to hardware. So yes, this is a simplification where each of these arrows traps down and then is forwarded to the inner one, which emulates. And in this process, essentially, you're emulating what the real hardware does on an exit.
So the question I had from reading the paper, which is, when you trap into the outer VMM, how does it know where to transfer back into the inner VMM? What's the mechanism by which it understands where the inner? I mean, do you presume that the inner VMM is the same VMM as the outer VMM? I assume not.
No, there's completely different VMMs.
Right.
There's internal state that it maintains, such that on each exit it knows which code was running when the exit happened. There's also another OSDI paper on that describes the same, roughly the same approach in a lot of details. But there's
it's in the references to your paper?
Yes.
Or? Oh, okay.
Yes, and it's right here. The citation there.
Thank you.
That gives an overview of how to use a single level of virtualization to virtualize multiple levels.
Okay, I'll look at that. Thank you.